All right, in the last video, we defined what a subspace was. In this video, we'll be doing example 1.2.1. So in that example, I'm going to take V to be the Euclidean vector space of dimension 3, so vectors with 3 components. I'm going to take W to be the plane 2x minus y plus z equals 0. I want to show that W is a subspace of V. So here is the condition to be in W. All right, so what I need to do, according to the definition of subspaces, I need to prove that W is a vector space under the addition and the scalar multiplication of E3. So regular vector addition and regular scalar multiplication of vectors. So that means that we need to prove the 10 axioms of vector space. For W. All right, let's start with axiom 1. Axiom 1 says that I can add 2 elements of W and still get an element of W. So I'm going to take W1 and W2 in W. So in W really means that this is true. So 2x1 minus y1 plus z1 is 0. And the same thing is true for x2, y2, z2. We need to show that the sum which is x1 plus x2, y1 plus y2, z1 plus z2. Again, I'm just using the operation of the bigger vector space. So I need to show that this sum is also in W. Right? So I need to check this condition of the star here. So 2x minus y plus z, this is equal to 2x1 plus x2 minus y1 plus y2 plus z1 plus z2. I'm going to split this, put all the x1s on one side, the y1s with it, and the z1, so all the ones. And everything that has a 2 subscript, I'm going to put on the left. All right, so I'm going to use the 2 conditions I had. I'm going to use 1 and I'm going to use 2. 1 is going to tell me about this guy, 2 is going to tell me about this one. I'm going to get 0 for one and 0 for the other one, so I do get 0. The star condition is true for my sum, and so this sum is again an element of W. All right, axiom 2, I need to show that the sum is commutative. Well, we know that that's true for V. We know that that's true for R3 because R3 is a vector space. But it's the same addition, so if it was true for all vectors in R3, it's certainly true for the part that satisfies the star property here. So this is true since it's already true for V. All right, similarly for axiom 3. In axiom 3, we have to look at associativity of the sum. So we need to compare this side with the same expression but parenthesized differently. But these are elements of W, which are elements of V, and we know that in V it's true, and so this will be true since it is true for E3. All right, and now you're starting to see a pattern. Because we already know that these operations are nice on the bigger set, they're going to be nice on the smaller one. And so many of these axioms we won't actually need to prove um, every time. All right, axiom 4. I'm going to take a zero element. I need a zero element for W. Well, I mean, I'm going to take the zero element of V. I need to show two things. I need to show that it is in W. That's not clear for all subset. And then I need to show that it has the right property. So first, zeros in W. So this is 0, 0, 0. I need to check the star property. So I get 2 times 0 minus 0 plus 0. I do get 0, so yes. And second, I need to show that if I add anything in W to 0, I get W back. Well, this is true because it is true in E3. All right, I'm taking the same 0 vector that we had in E3. So let me write it this way. And so it has the right property. I just needed to make sure that it was in W2. All right, so we've done 1, 2, 3, 4. Let's check 5. For 5, I need to find a minus element. So if W1 is x1, y1, z1, with 2x1 minus y1 plus z1 equals 0, I need to check that it's inverse, which is minus x1 minus y1 minus z1. I need to check that it's still in W. So I need to check 2x minus y plus z. That's going to be 2 times minus x minus minus y plus minus z, 1, 1, 1. Oops, sorry. Let me move this here so I can have a little more room. Otherwise, I'll keep hitting the side of my iPad. All right, minus z1. That's minus what we had. And so it gives you minus 0, which is 0. So yes. And then second part, what happens if I add W1 to minus W1? Well, it's the same minus W1 that we had in E3. And so it's going to give you the 0, sorry, wrong color. It's going to give you the 0 of E3, which is the same as the 0 of W. And so we're good. Notice that I'm doing the reduced axiom 5 with only one side check, but we've seen in the worksheet that that's the same thing. All right, axiom 6. Honestly, that's the last one where we really need to work. I'm going to take W1 as usual, x1, y1, z1 in W, and so I know 2x minus y plus z gives you 0. And I'm going to take k in R. Then k times W is kx1, ky1, kz1. I need to check that that is in W. So let's check 2x minus y plus z. That's going to give you 2kx1 minus ky1 plus kz1. And so that's going to give you k 2x1 minus y1 plus z1, k times 0, which is 0. And so kw is in W. The remaining axioms, axioms 7, 8, 9, and 10, are just on how nice the operations are. So they only depend on the operations. We know they're nice because we've already proven all the right properties for E3. And so these four axioms, they hold for W because they already were proven. They already hold for all of E3. And so we're done. Let me shrink this just a tiny bit so we can add the conclusion. I'm sorry, um, should have had more room. So hold for all of E3, and so W is indeed a subspace of E3. The important thing to remember here, the important thing to realize is that when you're proving, if you have a subset W and you're trying to prove that it's a vector space, axioms 2, 3, and 7, 8, 9, and 10 will come for free if you're using the same operation that you had in V. If you're using the same addition and the same scalar multiplication, then all of the properties like commutativity, distributivity, they will come from V and will be true in W as well. And so when you want to prove that a subset is a subspace, you don't need to prove the 10 axiom, which is why it's a nice way of getting more examples. In the next theorem, in the next video, we will actually show what you do need to prove to show that a subset is a subspace. It will be much less than 10 axiom. It will be only 3 properties, and that will save us a lot of time. All right, see you next time.